Okay, let's start. So today we will continue explaining the simple linear regression. Okay, so we'll talk about prediction, extrapolation.
Hello.
What are the differences?
Hi guys.
Hi, Dine. Do you have something to say?
Hi, I'm back after a few days. I'm sorry I missed some of your classes.
Oh, it's all right.
I'll catch up with the videos.
Okay. Okay, so today we were talking about what is difference between prediction and extrapolation. Okay, so what is the use of running a linear regression? So previously we discussed about we discussed about this a little bit. So using a linear regression, we can say that we can assess the association between two variables. Okay, we can assess the relation, the association between the response variable and other variables, other explanatory variables. So that is one aspect of running a linear regression. The other aspect is called prediction. Okay, so we can predict using our linear model based on our sample. Okay, so there is called prediction. Okay, so using the linear model, we obtain from our sample, and then we can predict the value of response variable for a given value of the explanatory variable, something like this. And how do we predict? We just use the value of any. I mean, if you have any value of interest for x or explanatory variable, we can plug in that value and then calculate the predicted value for response variable. Okay, something like this. Okay, so in our previous example, we already looked at the percentage in living poverty as well as percentage in high school graduation rate. Okay, so in this example we want to know that what if high school graduation rate is 82%, and the question is what is the predicted percentage living in poverty in states. Okay, so we will use the formula which we obtain from the linear regression. Okay, so we say that the predicted percentage in poverty is equal to this 64.68 minus 0.62 multiplied with percentage of high school graduate. Okay, so we just plug in this value, 82%. And then what we get is 13.84%. Okay, so the interpretation is when the high school graduation rate is 82%, then the percentage in poverty is expected to be around 14%. Okay, so this is called prediction. Okay, this is called prediction. Okay, what if we give the value something outside from our original data? Okay, that is called extrapolation. Okay, so prediction is when you given a valid value, okay, to the explanatory variable. Okay, what is a valid value? Which is within the range of our original data. If it is not in the original data range, and then we call it an extrapolation, which is not good. Okay. Okay, so from our data, we have this small one. Okay, and which we already look at as a scatter plot, but we extrapolated it to outside the range, okay, outside the range of the original data. So why it is not good? Because if it is beyond our original data, we don't know if the relationship is still linear or not. Okay, it can go either way. We cannot say that this will continue on a red line up to 0 on x-axis. Okay, so that is called extrapolation, and extrapolation is very bad, and you shouldn't do that. You can do prediction, but should be within the range of your original data. Okay, so according to this linear model, what is the predicted percentage of living in poverty in state where the high school graduation rate is 20%? Okay, similar to our previous example, we just uh, plug in the value. Because we have the value, we have the formula. But imagine that our data only provide more than 70%. Okay, but what we want to find out is 20%, which is far beyond here. So that is definitely the case of extrapolation. So using the mathematical formula, we can calculate and we can get a value. But as a researcher, you have to think that this value is appropriate to interpret or not. Okay. Okay, so that is prediction and extrapolation. Let's talk about the conditions or assumption that we use for linear regression. Okay. Okay, so what is number one assumption? As the name suggests, it is linearity, because the relationship between the explanatory response relationship is really important. Okay, it should be linear. What is linear? It means straight line. Okay, if it is not straight line, then we have a problem. Okay, so how methods for fitting a model to nonlinear relationship also exists. Okay, so if it is not linear, we have to think about other possible nonlinear model, okay, to run our analysis. But first, we have to consider the linear model. Okay, so how to check the linear model? So we can use scatter plot, okay, which we have already looked at, and we can also look at the residual plot. Okay, we already know what is a residual. What is a residual? Okay, so these plots, so plots on the top are scatter plots. Okay, the ones below are residual plots. And so these correspond to each other. Okay, so let's see this one. Let's see one by one. Okay, so as you can see here, it's exactly, there is linear relationship. Okay, and then you can see that there is not a lot of scatter. Okay, almost everything is on the same on the straight line. So when you see data on a scatter plot and you plot the residual and the fitted value, okay, we will talk about this later, okay, about the about residual in detail later. But right now, think about this as a residual. Okay, what are residual? Residuals are the difference between this point and the observed value and the predicted value. Okay, so we subtract these residual, the distance or the gap. So as you can see that, so you know that this is something like the standard deviation. Okay, so it should be center around 0, because the center around 0, and you can see that these points, there is no obvious pattern. Okay, there are no obvious pattern. Okay, let's talk about the second plot. So we fitted a straight line, but this is not a straight line. Okay, it has a little bit curve. So this relationship is not entirely linear. And when we plot the residual, you will see a pattern something like this. Okay, And here on the dot plot, we have various, I mean, the points are really scattered all over the plots. So there is not much change in the linearity, okay? But you see the residual, I mean, this width is more broad, okay? This one is a little bit narrow because the points are not that scattered. But here it's scattered over the, all over the place. So you got a lot more variability in the residual. Okay, so this is how you check the linearity assumption. Okay, so you use scatter plot and look at the residual plot to see any patterns. Okay, if there is any pattern. If it is randomly scattered, then we can call it a linear association. So comparing this, the last plot and the second plot, this one can be considered as a linear because the pattern are not, there is no pattern, it's random. So in a second plot, there is obviously a shape, there is obviously a shape in a residual plot. Okay, so this is how you check linearity. So next, we look at the anatomy of the residual plot. Okay, what is a residual plot? So basically, this is a scatter plot, which we have already discussed the other day, okay? And this is the scatter plot. So on x-axis, we give the percentage high school graduate, and on y-axis, we give the percentage in poverty. And then in the residual, we on the x-axis, this is the predicted value, and on a y-axis, this is the residual. Okay, so this is the residual plot. Okay, this one is the scatter plot. So as you can see that we pick out 2 points. Okay, the first point is the green point, which is the RI, okay, Rhode Island, and the second one is this DC. So these are on either side of the straight line. So we just want to show them as an example. So let's look at the this example. Okay, so in this scatter plot, percentage of the poverty is 10%. Okay, the high school graduate percentage is here around 81%. Okay, something like this. Okay, let us put a line here. Okay, so this is how we get the number. Okay, and then we give this value to the formula that we obtain from the linear regression, and then calculate the calculate the result, and then we come up with the 40.46. Okay, so what is the 40.46? It is the gap between this point and the line. Okay, so the green line. So this one is the green line. And then what we do is okay, sorry, this one is on a point, and this residual is the green line. Okay, so this is the distance between the observed value and the predicted value. So that is what we point, and that is what we plot here. Okay, so here we have the residual, which is minus 4.16% above the zero. Sorry, below the zero. Okay, for the DC, which is obviously above zero, so which is 5.44%. So this is how you draw on a residual point. But don't worry about it. We don't have to draw it manually, or even in R. We can just type a command, and this plot will be automatically plotted. So you just have to understand how to check the linearity and interpret the plots. Okay. So the second assumption is near normal residual. Okay, the distribution of the residual should be normal or near normal. Okay, so we already talked about this. Okay, we already talked about a normal distribution. So this concept shouldn't be difficult to understand for you at this point. So this may not be understand if there are unusual observations, something like outliers, okay, that don't follow the trend of the rest of the data. Okay, so we can check the histogram of the residual, okay, and see if there is normally distributed or not. Or we can use the quantile plot, okay, of the residual. Okay, so in our software we use this plot. So here we can say that okay, there is not it looks normal, so we can say that it's closely close to normal distribution or nearly normal distributed. Okay, number 3 is the constant variability. Okay, so the points scattered around 0 should be constant. Okay, and this implies that the variability of residual around 0 should be roughly constant. And this is called a homoscedasticity. Okay, it's a little bit twisted word, but it is called homoscedasticity. But you can say that it is the constant variability. Okay, so we check using a residual plot as well. Okay, so this is a scatter plot, and you can see that so there is a gray band that indicate the variability of the point. Okay, and when we plot the scatter when we plot the residual plot, you can also see that the residual is between 4 and -4, and it's constant around it's constant across x-axis. Okay, so in order to understand this, we can I'm going to demonstrate this. Okay, so what I will do is I'm going to give this a link, copy these links, and okay, so look at the chat box. You will see the link, and you can play around it. Okay, but right now, just I think follow this webinar. You can play around it on your own time. Okay. So anyway, what is this is just the just to give you an idea of how different diagnosis for different linear regression. Okay, I mean for different data. So if the data is linear, if it is a positive linear association, if it is negative linear association, how it appears in the residual plot and histogram, and also the normality plot. Okay, or if it is a curve pattern, how it will appear. Okay, so we will just take a look at this. So you can see that it is the diagnostics for simple linear regression. Okay, we call it diagnostics, like a doctor diagnoses a patient. We have to diagnose our regression model, whether it is fit to use and interpret our result. Okay, so this is very important in our modeling process, because modeling you have to just type 1 or 2 lines of comments in R, and then you will get a result. But the art of interpreting the regression model is an art. Okay, so you have to learn it. So we already seen this kind of this is the scatter plot. Okay, so this value are coming from regression model. Okay, so at this moment, just forget R squared. Okay, just look at the R value. So R is basically 0.7911. So basically it's a positive association, positive linear association. So we can say that, okay, it's fairly strong association between X and Y. Okay, and then here there is there are some legends. Okay, so blue indicate regression line, and gray area indicate confidence interval, and then this lighter color indicate the prediction interval. And anyway, so the data shows the positive association, and you can see that the variability is constant, okay, as the X value increases. Okay, so if it is the case, then when we look at the residual as a fitted plot, okay, fitted value. So on y-axis, we see the residual. On x-axis, we plot the fitted value, okay, and so this is the residual plot, and you can see that there is no pattern, okay. All plots, all points, data points are randomly scattered around 0, so it's quite okay. So the first assumption, linear assumption, is okay, okay, and the second assumption, residual normally distributed or not. So we can say that, okay, this looks fairly normal, or we can look at this, okay. So you can see that the data points are all on a straight line, okay, all on this straight line. So we can say that, okay, these residuals are nearly normally distributed. Okay, the third assumption, which is the constant variability. So you can, if you look at the scatter plot, you can see the data points are scattered, I mean, equally across the range of X, okay? And here, it is also, there is no pattern, okay? The same case, if we choose here to linear down, okay, which is a negative linear association, and basically the same interpretation. Okay, let's look at the curve F, okay? So this is obviously not a linear regression, a linear association, okay? It is the curve association, which is a quadratic association. And now if you look at the residual, you can see these are the patterns, okay, that we are talking about. So you should look for these kind of patterns. If you see this kind of pattern, then this violate the assumption, okay, linearity assumption. And if violate the linearity assumption, you can see the residual does not, the residuals are not constantly varied across fitted value, okay. It will just go down and up, and you can see there's a little bit right skew, and on a plot it is it's not normal distribution, okay. The same uh, the same can we see, okay. So there is an option here, okay, show residual. So which is basically when we click it, this will show the residual here, okay, in red line. Okay, you can play around it, okay. So the same interpretation can be made. So this is not linear association, there is no constant variability, and residuals are not normal, okay. So all violates linear assumption for simple linear regression. Okay, so the last one is peculiar, okay, which is a fun shape, okay. Okay, so what is a fun shape? It's a fun, right? So it's a fun, that means that it will go broader, and as the value is becomes bigger, okay. So this is basically called a fan shape, and this is more obvious when you look at the, okay, wait a minute, when you look at the residual plot, okay. So you will no longer see the random scatter, you will see a fan shape scatter. So which obviously violates the linearity assumption, okay. And the variability are not constant either, okay. It just, you know, increase or decrease when a filter value increases, okay. So we will say that, okay, this violates the assumption for linear regression, okay. So this is how you do diagnostics for simple linear regression. Okay, let us go back to the PowerPoint. Okay, so I sent a link via the chat box, so you can play around when you have time if you are interested. And then let's continue talking about the how we understand our model. Okay, so we know the conditions. We know we already checked the condition, and then we have to think about, okay, we have the data, we fit the data using a model, linear regression model, and how well this model explain our data. Okay, this is called R square. Okay, so which is basically the same as square of correlation coefficient. Okay, this is R square. So what is the R square? So we use this to evaluate the strength of the fit of linear model. Okay, whether it fit our data well or not. So how do we calculate? We calculate as the square of correlation coefficient. Okay, and then it tells us what percentage of variability in a response variable is explained by the border. Okay, so as of now we only have one explanatory variable, and then we fit the data to using our model, and then we calculate R square, and we want to know, okay, how much this variable explain our data. Okay, explained by the model. So basically the rest of the variability we cannot, I mean, we don't know. There are other variables we have not collected in our study or which not included in our model, so we don't know. The rest are like black box. Okay, so we know that, okay, a certain percentage of variability in our model can be explained by this response variable. Okay, we included in the model. Okay, so anyway, if we square this is always between 0 and 1, because R is always between +1 and -1, right? And then when you square it, it will always be a positive value. And then when you multiplying 2 percentage point, okay, you will get a smaller number. So it will always be between 0 and 1. Okay, so let's think about it. So the correlation of percentage in living in poverty and percentage of high school graduate was -0.75. Okay, what is R squared? So it is obviously easy, right? So when you square it, there won't be any negative value. So you just delete a negative value, and then think about it. Okay, you just multiplying this value twice, so the correct answer is this one. Okay. Okay. Anyway, this is just a math question. Okay, so this one is the correct answer. Okay, so we now know that the R square value is equal to 0.5625. So how do we interpret this? Okay. Okay, so the first we try this. Okay, 56%, 66.25% of the time, high school graduate percentage living in poverty correctly. This is not correct. Okay, this is not correct because we're not talking about the data point, our original data point here. Okay, so this is not correct. And the second one, 43.75% of the variability in percentage living in poverty among the states is explained by the model. And the interpretation is, I mean, this sentence is correct, but the value is not correct. Okay, the value should be 56.25. So it's not the opposite. Okay, so this is still not correct. And then we look at this one, 56.25% of the variability in percentage of high school graduates. Okay, so R squared is only about the response variable, not the explanatory variable. Okay, so it should be about the percentage, poverty percentage, not the high school graduate percentage. So this is also wrong. So the final one, 56.25% of the variability in the percentage of resident living in poverty among the state is explained by the model, or explained by adding this percentage high school graduate to the model. Okay. The rest, 42.7%, we don't know. We don't know which which explain this percentage, because we do not have the data. So anyway, that is how you interpret it. So the next question is the R square for relationship displayed in the scatter plot is 92.16%. So what is the correlation coefficient? I think this is also very easy, right? So you just you can just use your calculator or open R software and just calculate the square root of this R square. Okay, so it will give you the value, this one, okay, minus 0.96, which is minus 0.96. Okay. Okay. Anyway, so we talked about the conditions and the R square, how to assess the fit of the model, and then we should also talk about the categorical explanatory variable. So as of now, what we discussed so far is two numerical variables. Okay. So what if our explanatory variable is categorical? How do we interpret it? Okay. How do we even run it? Okay. So let's see. So in this case, we will use another variable. Okay, which is a region. So the poverty percentage is a continuous variable, which we want to know. Okay, we want to know if there is any association between a region and the poverty percentage. So our explanatory variable is region, and we have only two regions, east or west. Okay, so linear regression, if you remember, it is a mathematical expression, right? So we use it. We can use arithmetic operation. We have to use arithmetic operation in order to come at the final numerical value. So we cannot put the character east or west. Okay, so we code that east as 0 and west as 1. Okay, as a symbolic nature, but also we can also use as an arithmetic operation so that we can come up with a final value. Okay. Okay, so let us plug in this. So we ran the linear regressions and we found that the formula is the predicted value of poverty is equal to 11.17 plus 0.38, region is west. Okay. Okay, so how do we plug in the value? So we already have coded east as 0. So when we plug in 0, the poverty percentage is 11.17%. Okay, so we plug in 1, which represent the western states, we got a poverty percentage of 11.55. Okay, so you don't need to have a whole range for categorical variable. Okay, we only have to have 0 and 1. Okay, so when it is east, okay, when it is east, we got a poverty percentage of 11.17, and when it is west, we have a poverty percentage of 11.55. Okay. Okay, so because we already ran the linear regression, we have the intercept and slope. Okay, so the intercept is when the region is 0, which is eastern state. Okay, when the region is eastern state, the model predicts 11.11% average poverty percentage. And then what about the slope? Okay, so the slope is the slope explained about the western because it indicates by 1. So when it is the slope, okay, when it is the western states, the model predicts that the percentage poverty percentage is 0.38% higher than the eastern state. Okay, so when you interpret the categorical variable, there is always a comparison. Okay, So when we interpret the numerical explanatory variable, previously we say that, okay, if there is an 1 unit increase in explanatory variable, then we will see some value decrease or increase in response variable. Okay. However, in categorical variable, it is different. Okay, so we have to compare to each other. So compared to eastern state, okay, if it is the western state, then the percentage of poverty percentage is expected to be 0.38% higher. Okay, this is a comparison. Okay, so what if we have 4 regions? Okay, previously we talked about only 2 levels of categorical variable. What if we have 4 levels? Okay, we have north, east, midwest, west, and south. Okay, 4 regions. So we ran the linear regression and we came up with this coefficient value. Okay, so estimate these are the intercept and slope, and then standard error, t-value, and p-value. Okay, so anyway, when we write the formula, we come up with the formula like this. Okay, so percentage of poverty is equal to intercept plus, okay, and then slope multiplying with corresponding level. Okay, multiplying with corresponding level. Okay, so what is the reference level in this variable? Okay, the reference level is not the reference level is the level that is not in this category. Okay, a comparison, and we should have one level. We should keep one level as a comparison. Okay, so here the level which is not here is the comparison, is the reference level. Okay, which is the northeast. Okay, which is not in this list. So which is basically 0. Okay, which is basically 0. Everything in this list is set as 1. Okay, 1, 1, 1. Okay, so how do we interpret this? Okay, how do we interpret this categorical variable? So first, we will calculate the predicted poverty rate for Western state. Okay, for Western state. So we want to look at the Western state, and then the rest should be 0. Okay, the reference category is already 0. But we have 2 more regions, Midwest and South, okay, which we will keep as 0. So that is what we say as when we keep the same value for the other 2 other levels, and then we interpret the West. Okay, so we want to know the West, so we gave it 1 to the West, and then 0 to 2 other levels, and then we calculated it is 11.29%. Okay, so how do we interpret this? We interpret it, okay, by setting the same value to other other variable, to other levels, compared to the northeast states. The poverty percentage is expected to be 11.29% when it is in the Western state. Okay, so that is how you interpret it. So we keep the same value for the other 2 level we are not interested in anymore. So okay, so this is how you will get if you have multiple levels in a categorical variable in a linear regression. Okay, so we already talked about conditions, but we need to look at other things too. Okay, not only check your conditions or assumption for linear regression, we also have to look at the outliers. Okay, because do you remember we have a lot of calculation, correlation, and even with the calculation of intercept and slope, we use the mean, and we use the each points, okay, to calculate the errors and everything. So outliers are very important, and linear regression is very sensitive to outliers, okay, and we will discuss more. Okay, look at these two plots. Okay, the plot on top is the scatter plot, which we have a single outliers, and the lower plot is the residual plot, which you can see that this one is separated from the rest of the data points. Okay, so if we remove this point, there is no relationship between x and y. Okay, because it is quite, randomly scattered. But you see a single outlier value pull the slope towards it. Okay, so if you only look at the slope, you will say that, oh, okay, there is association. So that's why you need to look at the scatter plot and data exploration before you do uh, any modeling. Okay, so these are called outliers. Okay, so what are outliers? Outliers are just points that that are separate from the rest of the data points. Okay, so if this outlier fall horizontally, okay, if you look at the horizontal data point, if the data point is horizontally away from the center or the rest of the data points and do not influence the slope of the regression, it is called the leverage point. Okay, we will illustrate it with graphs in a moment. And then if it is these are outliers and it fall horizontally away from the center and also influence the slope of the regression, then we call them influential points. Okay, these two are very important. Okay, outliers are important, and you have to know which are leverage points and which are influential points. Okay, so leverage points, they are horizontally apart from the rest of the data points, but they don't influence the slope. So basically it means that it does not change the slope even if we remove them. But if we remove them, if it changes the slope of the regression line, we call them influential points. Okay, so these influential points are usually high leverage point or potential leverage point. Okay, and then we determine how do we determine if a point is influential? We visualize the regression line with or without a point. Okay, so first you look at the scatter plot with the regression line with all the data, and then second you plot the same scatter plot with regression line without or removing the outliers, and then see if the slope changes. If it is changed, then it is influential point. If it is not changed, it is leverage points. Okay, so look at this. This is a scatter plot, and there is one point. Okay, and then you can see that this is horizontally apart. Okay, apart from the rest of the data point, and then even when we change it, okay, even if we remove it, this slope will not change because you can see that it is neatly on a straight line. Okay, the rest of the data point is on a straight line. So even if we remove this point, this will not change the slope of the regression line. So we call this as a leverage point. Next, we still have the single outlier, as we see in the previous plot. Then when we remove it, this plot were flat. Okay, there is no association basically. So we can say that it is highly influential on the slope. Okay, so this is called an influential point. Okay, so look at this example. Okay, we look at this example. So on the x-axis we see that there is a logarithm. Okay, natural logarithm of temperature, and this is a data transformation. Okay, and then they plot the data points. And this is the light intensity and transform and log transform. Okay, so light intensity in a surface temperature, log transform of 47 star in a star class star something. Okay, this coming from astrological data, astronomical data. So there are 47 stars. Okay, 47 points. Okay, so let's take a moment and see what color indicates what. Okay, so red line, what red dotted line indicate with outlier. Okay, blue solid line indicate without outliers. So you can see that the data is these 4 data points are horizontally away from the rest of the data. Okay, so you can see that if we do not remove the outlier, the slope say that okay, it is the negative association. Okay, and it's really interesting, right? And then we remove the outlier, and then the slope becomes the positive association, pretty strong, huh? Okay, so how do we analyze in this kind of plot? Okay, so the way we I mean, outliers are pretty interesting. So these are strange phenomena. So you have to investigate them separately and look them. Okay, if it is an error during data collection or data entry, if it is not, if it is real and if it is solid, then you have to use it. Okay, you cannot just remove it because they are just because they are outlier. So how do we analyze this? So you analyze separately. Okay, so you separate the 2 groups and then run regression model on each data on each group. Okay, so for this group, we will say that that is strong. So we separate groups into high and low temperature. Okay, so regarding high temperature, we get a positive regression line, linear regression line, and on this one we got something. Okay, some line. Okay, anyway, these are influential points. Okay, that drastically change the slope of the regression lines if we remove them. Okay, so the question here is, if we remove influential points, it always reduce R square. Does it always reduce R square? Okay, so I think we can say that if there is an always word, then we can say that it's wrong. Okay, it's not always it does not always reduce R square. So we can see here that this without or without the outlier. Okay, and the slope changes pretty much, and then you can see that the I mean, there is no linear pattern on this data. Okay, and if we look at the R value is 0.08, okay, and then R squared is 0.006 if we remove the single outlier. Okay, if we do not remove the single outlier, it is, I mean, it is like, you know, many times greater than this one. Okay, so removing the outlier does not always reduce the R squared. Okay, it depends on where the influential point is. Okay, okay, anyway, let's move on. Okay, so this will be false. Okay, so which of the following is true? Okay, influential points always change the intercept of the regression line, and influential points always increase R squared. And the third one is, it is much more likely for a low leverage point to be influential than a high leverage point. And number 4 is the one, the data set includes an influential point. The relationship between the explanatory and response variable is always non-linear. So which one is the correct answer? So we can say that, okay, this is A, B, C, D, E. So take a moment and which one do you think is the correct answer? Okay, I got some answer. And one side A and one side E. Okay, so A is the correct answer. Okay, A is the correct answer. So which means that it is not incorrect. Okay. Okay, so inferential points always change the intercept of the regression line, which we already seen it. Okay, I mean, I said if it is always there's a word always, and it is not always false. Okay. Anyway, let's look at the okay, so here we have an inferential point. So when we remove the inferential point, we have the intercept change, right? So in this plot, the intercept is below 0, and when we remove it, the intercept changes to value greater than 0. Okay, so this one is true, and always true because why? Because inferential point always change the slope. Okay, that is the definition of the inferential point. Always change the slope. So which means that it will have different different intercept. Okay. Okay, so the question here is how do we interpret R and R square here? Okay. Okay, let's look at the second plot. So R here is a correlation coefficient. Okay, so correlation coefficient, we can say that there is a this one is positive and this one is 0.7, so it's fairly strong. So we can say that it is a positive linear association, fairly strong linear association between this one and this one. Okay, X and Y. And how do we interpret R square? So R square is the percentage of variability explained by the X. Okay, given Y is the response variable. So we can say that, okay, the around 62% of the variability in predicted this Y response variable can be explained by the model by adding X. Okay, so the model is doing pretty well, is 62%, so not bad. So here you can see that we remove the outlier point, so there is no, it's almost 0, so there is no linear association. Okay, we say there is no linear association between X and Y, and R square we are not there yet, Denise. We are not there in logistic regression. Okay, anyway, in logistic regression, we do not calculate R square. Okay, I mean, R square is basically square of correlation coefficient, and logistic regression is basically the outcome is a binary variable. So there are a lot of there are other several other criteria which we can say how the data fits well. Okay, and we will discuss more, but this is the basic. Okay, and even with the linear regression, we do not use R square all the time. Okay, because there are limitations of using R square, which we will discuss in due time. So we have a lot more to discuss. Okay, this is on day 2, and usually when we look at the model, we use other criteria such as other value, like we have a few other values like AIC value, BIC value, and even sometimes we use the square root of the mean square error or something. Okay, MSE. Okay, basically we will talk about in due time, but I think let's discuss about this in logistic regression. Okay. Right now, this is how you interpret in this context. Okay, so basically, if there is an outlier, it is not an appropriate interpretation. Okay, because there is an outlier, it is not true. Okay, the data is not explaining well, so you have to remove the outlier, and then look at the R square. Okay, it's barely 0% explaining the variability by the model. Okay, anyway. Okay, anyway, the correct answer is the inferential point. Oh, wait. Okay, maybe I am wrong, sorry. So inferential points change the slope. Okay, so I was wrong. Okay, so none of this is correct, okay? So like I said, if there is or is, then it is wrong. Okay, so inferential points change the slope, not necessarily the intercept. Okay. So they can reduce the R square if the remainder of the data show a strong relationship, and there is only one or few points that are outside the trajectory of the regression line. Okay, then high leverage points are more likely to be inferential. Okay, so I was wrong. So I think who is that? Shiwan, he is correct, choosing E. Okay, anyway, these are some quiz. Okay, so next, what we are going to discuss is the inferences for linear regression. So as of now, we talk about how to calculate the slope and intercept, but we still need to talk about how inferential statistics works on this linear regression. Okay, so it's a little bit in depth, but I think you will appreciate the the mechanism how uh, we calculate the confidence interval and p-value in the context of linear regression. It is the same. Inferential statistics basically calculating is the same. So we talk about hypothesis testing and then confidence interval for the slope and condition for inferences. Okay, so there is a study. There is an example of a study in 1966. They look at the genetic determination of differences in intelligence. So the population, the sample is monozygote twins, okay, which are twins, but they were raised apart. And then they look at the intelligent IQ score, okay. So the data consists of IQ score and assume random sample of 27 identical twins, one raised by the foster parents, so one raised by the other raised by the biological parents. So they make a scatter plot, and then on x-axis we have the biological IQ, and then on y-axis we have the foster IQ. And you see that there is as the biological IQ increases, then the the IQ of the children raised by the foster parent also increases. Okay, so correlation coefficient is fairly significant. Fairly strong association. And then when we look at the regression output, we want to predict, okay, the IQ score of the children raised by the foster parent based on the IQ score of the children raised by the biological parents. So we fit a linear model and say that, okay, there is a if there is one unit increase in IQ score, then the foster IQ will also increase 0.9 unit. Okay, so this is basically the idea, the interpretation of the slope. And then we calculated R square, and R squared is roughly 0.78%. So we can say that, okay, the foster IQ, okay, the variability in foster IQ about 78% can be explained by biological IQ, okay, or by the model. And then if we look at the p-value is significant, okay. Okay, here's a question. So we have the model output and then see which of the R squared is 78% and which of the following is false. So we'll look at one by one. So for each 10 point increase in biological twins, we expect the foster twin IQ increase average by 9 points, which is correct, right? So when you increase 1, then it will increase by 0.09. 0.9. So which you multiply with 10, then it will increase by 9 points. Okay, so this is correct. We need to find the fourth answer. So the second one is the linear model is this one. So this is also correct. And roughly 70% of the twin can be accurately predicted by the model. Okay, so I did this wrong because we cannot say that we cannot. Well, the R squared is not about the data, about the sample. Okay, the R squared is the variability explained by the model. Okay, so 78% of the variability in Foster twin IQ can be explained by the model. So this is wrong. And then Foster IQ with Foster twins with IQ higher than average IQ are predicted to have biological twins higher than average IQ as well. So this is also correct, right? Which is a positive association. Okay. So okay, so we have these coefficient estimate. So how do we test that these slopes and the result are not due to chance? Okay, so so we will say that okay, the null hypothesis is our slope is equal to 0. Okay, there is no association, so the slope is equal to 0. And alternative hypothesis is something is there. Okay, so it's just not equal to 0. It can be greater than 0 or less than 0. Okay, just not equal to 0. And then we use the same formula that we have seen in calculating the T statistics or Z statistics previously. Okay, so basically the formula is the same. We use the observed value or the point estimate, and then we subtract it with the population mean, and then here in this case it is the null value and divided by the standard deviation or standard error. Okay, and then when we put it corresponding value, then we got this t statistics for the slope. Okay, which is basically point estimates is our slope which we obtain from a linear regression model. And then we want to see the null value is, the null hypothesis is the slope is equal to 0. So that is our null value. So null value is 0. And then we see the standard error of the slope. Okay. And then we need to calculate the degree of freedom is 2. Okay. Because we have the 2 parameter, which is slope and intercept. Okay, so how do we calculate this? We have a formula and then we just plug in the value. Okay, we just put the value there, and then see T is 9.36. Okay, you don't have to calculate manually. I just want to give you an idea how this works. Okay, so when you have estimated standard error, you already got a T value and P value. Okay, and then when you got a T value, when you got a standard error and estimate, then you will get a 95% CI. Okay. So basically, the degree of freedom is calculated by the total sample size minus 2, which we have 2 estimator, okay, intercept and slope, which is 25. Then we calculated p value, okay, greater than this t value when the degree of freedom is 25, and is approximately to 0 because you see p value is greater than 3, way beyond 3 standard deviation. Okay, so this is 9.36. So we say that okay, this the probability of getting an extreme value like this, given the null hypothesis is true, is approximately equal to 0. So we will reject the null hypothesis. Okay, and say that there is an association between biological IQ and forced IQ. Okay, so this is the that was the hypothesis testing p-value, and let's look at a confidence interval for the slope. Okay, so how do we calculate the confidence interval for the slope? We have a point estimate, and then we plus or minus marginal errors. Okay, and then we convert this into the formula. So point estimate is the slope p1 plus or minus, and then we calculate our marginal error, which is comprised of the critical value, if you remember, and critical value multiplied with the standard error. Okay, so critical value in this case is a t distribution with degree of freedom. Okay, and then standard error. So we this one is not a t here. Okay. Okay, basically, we will look at this. Okay, so we will calculate the 95% CI. So we draw the graph, and we want 95% CI. So we have the lower tail at 0.025, and then we have to look at the quantile of the t distribution. Okay, this is not z distribution, so it's no longer 1.96. Okay, so we have to calculate the quantile of t distribution. So it's qt. Okay. Previously, we look at the normal distribution, okay, probability or normal distribution, which is P norm, and quantile about the normal distribution, which is Q norm. Okay, in this case, it is the T distribution, so we use QT and give the value of the probability, and then we add give the degree of freedom, which is for 95% CI, T value is minus 2.05. Okay, so we were used to calculate 95% CI for the slope. So you just give put into the formula, and then we got 0.7 to 1.1. Okay, so how do we interpret this 95% CI? Okay, so as we interpret any 95% CI, we will say that we are 95% confident that for each additional increase for any increase point in biological twins IQ, the 4-star IQ increase on average is expected to be higher between 0.7 to 1.1 points. Okay, so this is how you interpret the confidence interval for the slope. And then, okay, to summarize this today's session, and we talk about the inferences for regression. So use same hypothesis test, okay, using the formula, but different parameter based on the context. And then we calculate the confidence interval based on this one. Okay, so this one and this one are not equal. Okay, you have to remember that this one is corresponding to 95% CI. This one is corresponding to p value. Okay, which is not the same. So okay, so I think let's go back to the confidence interval. We can also look at here. Okay, we can also look at the confidence interval and say something about the final conclusion, right? If you remember, if the null value, which is 0 in this case, okay, with the slope, our null hypothesis slope is equal to 0, right? So 0 is not within the confidence level interval. So we can say that, okay, it is significant, okay? This is quite good. So which is consistent with our previous lesson. Anyway, so regression outputs gives out the slope, standard error, and then this p value is null value is 0. Okay. Okay. Anyway, this output will be given by the this output is by the base R. But when we talk about the linear regression function in MSTAT, this will be a little bit different. Okay. And I think we'll do that tomorrow. Here, before we conclude this today's session, we say that always beware of the type of data you're working. Okay, so whether you have the random sample or non-random sample or population data. If you have a population data, then you don't need to calculate confidence interval. Okay, and you don't need to test the statistical inference. Okay, because you already have the population data. And if you have a sample that's not random, then you have to be careful when you interpret the result, because which is unreliable, which means it's biased. Okay, so if you're writing a scientific manuscript, then you have to put it in a discussion as a limitation. Okay, this is a non-random sample, so the study has limitation. The result should be carefully interpreted. Blah blah blah. Okay, the last one is the ultimate goal is to have an independent observation, and which we already discussed in week 2, right? So you have to look at how you obtain the data, and then you have to look at the sample size, And then if you don't need to get very big sample size, okay, remember you need to sample size which is less than 10% of the population. So if you get that, you can assume that you have an independent observation. Okay, so I think we will stop here, and tomorrow we will just continue this PowerPoint, which we will talk about variability partitioning. Right now we've seen the variability, right? So the variability explained by the model and the variability not explained by the model. And this is another, this will lead to another, I mean, measure how we can assess the fitness of our model, okay? So here, there are different components, okay, when you run a linear regression. The first one is, okay, the first and foremost is you want to look at the slope, which is the purpose of our analysis, okay? Because you want to know the association between the response and the explanatory variable. However, in order to use the slope value, you need to check all the other assumptions so that your model is solid, your model is valid, okay? So in order to understand that there are several measures like R square, which we can evaluate our model. Okay, so we already know R square, and then tomorrow and then the day after tomorrow, we'll talk about other diagnostic measure which we can use in linear regression context. Okay, and this variability partition is also another measure which we can assess our model, basically. Okay, so any question at this point? I think this week we are a little bit heavy on, I mean, details, but I think you appreciate this detail when we really work on the, I mean, with our software and when you interpret the result, okay? So no questions like that? Okay, so that's it today. So we will see you tomorrow, okay? Stay safe and stay at home.